The material delivered in this session is copyright Specwall. Hello, and welcome to How Advanced Walling Systems Can Produce Sustainable Outcomes in the Built Environment, brought to you by advanced walling system manufacturers and suppliers Specwall. This session aims to explore evolving trends in walling system design and its relationship with sustainable construction methods. The net energy savings realised within off-site construction and sustainable material choices are now well understood, and these savings are increasingly required by stringent local building and energy codes. Further considerations around fire safety will also be discussed within the session, as the need for Class A rated construction materials continues to grow in light of recent changes within building regulation. We hope you gain value from the session. There will be an opportunity at the end to share your feedback on today's learning. We'll now take this opportunity to explain a little bit about ourselves. We're Specwall, and we're manufacturers of an advanced walling system of the same name. Our aim is to provide innovative and high-quality products that meet our customers' needs. We are sensitive to our most valued resources, our people, and to the environment, while maintaining our fundamental values and achieving long-term success. We're based in Manchester and have showrooms in both London and Manchester, and we're part of the Property Alliance Group and Harwell Group. Our advanced wall system is frequently specified into various commercial and residential settings, and over the past few years we've established ourselves as an innovative brand who are always looking to make the construction process more efficient, safe and sustainable. We really hope you enjoyed this session on advanced walling systems, and we're now going to take this opportunity to share today's learning aims and objectives. It's recommended that you make a note of these learning objectives and make reference to them throughout the seminar. There will be an opportunity at the end of the session to reflect on these learning points. Firstly, we're going to uncover the notion of designing out waste and its impact on sustainable practices within the built environment. We'll also take a look at the recent changes in building regulation and how they should influence your design strategy for producing fire-safe buildings. There will be also a chance to explore how advanced wall systems are being utilised in the construction of interior and exterior wall assemblies. And finally, you'll gain a better understanding of how these advanced systems are currently being installed on construction sites. We're now going to delve a little deeper into the roles and responsibilities of you, the specifier, in the reduction of construction site waste. Sustainability has risen rapidly up the construction agenda over the past few years. Designers play a key role in helping to deliver projects that are sustainable in terms of their environmental, social and economic impacts. And one important impact is waste, particularly waste arising during construction. Much has been implemented on ways to address the impact of design practices on waste generation, owing largely to the climate emergency declarations by the UK government in 2019. Within development management plans, many local authorities mandate architects, developers and clients to address sustainable design practices which design out waste prior to construction. For example, planning consent is sometimes given on the condition that the applicant's agent, i.e. the architect, provides site waste management plans, SWMP, before construction works commence on the site. Despite site waste management plans sometimes being requested by local authorities, they were repealed by government on the 1st of December 2013, following a consultation as part of the government's initiative to reduce red tape. There is little up-to-date research into architects' viewpoints on construction waste minimalisation, and it's often down to the individual practices to adopt their own practices and policies. However, in 2008, Osmani, Glass and Price examined previous studies on architects' approach towards construction waste minimisation, and by means of a postal questionnaire, investigated the origins of waste, waste minimisation, design practices in the UK, and responsibilities and barriers within the UK architectural profession. The findings revealed that waste management was not a priority in the design process. Additionally, the architects seem to take the view that waste is mainly produced during site operations and rarely generated during the design stages. However, About 1/3 of construction waste could essentially arise from design decisions. Results also indicate that a number of constraints, namely lack of interest from clients, attitudes towards waste minimisation, and training, all act as disincentives to a proactive and sustainable implementation of waste reduction strategies during the design process. We're now going to turn to a study conducted by sustainability charity WRAP.org.uk, who researched and identified the important contribution that designers can make in reducing waste throughout design. The diagram taken from RAP Figure 1 shows how this can be approached, and the yellow boxes highlight the areas where designers can have a significant impact. It is important that designers also adopt the waste hierarchy, Figure 2, that focuses initially on reducing waste, as this is where potentially larger impacts can be made. The efficient use of materials reduces the quantity of materials used in the first instance, lowers the material purchasing costs, minimises waste, and eliminates the need for subsequent handling and disposal costs. Developing a strategy to reduce waste is one of the most effective ways to address waste in construction. Once effective waste reduction measures are in place, it's then more appropriate to consider how to reuse, recycle, recover, or finally dispose of waste in a structured way. In summary, major improvements in materials resource efficiency are possible without increasing costs by reducing the quantity of materials being sent to a landfill during the construction process, by designing out waste and effective site waste management, reusing, recycling and recovering waste material as appropriate, and utilising more recycled materials and mainstream products containing high levels of recycled material, recycled content, including material not necessarily sourced from construction and demolition waste. If you work in the field of construction as an architect, a designer, manufacturer, contractor, consultant or investor, you have the opportunity to contribute to shaping the world of tomorrow by making smart design choices, evaluating materials more carefully, and relying on proven methodologies and metrics. You can find out which choices can result in buildings with a lower carbon footprint and use that information to continue improving your future projects. While green building is an ethical commitment to a better future, it is also a sound financial choice, as the market demands more transparency, more traceability and accountability. With sustainability in mind, we're now going to take a closer look at wall construction. Internal and external walls serve a multitude of purposes, including privacy, acoustics, fire separation, and flexibility of layout. Let's not forget that internal walls also act as wayfinding, allowing users of all ages and abilities to navigate safely around the building, making places convenient and enjoyable for everyone to use. For the purpose of this session, we're going to focus primarily on internal wall construction. But the wall construction materials covered in this presentation can be used for both internal and external assembly. Sound insulation describes the reduction in sound across a partition. As an example, the sound insulation across a good conventional, lightweight, office-to-office construction is typically in the order of 45 decibels. This means that if the sound level in the source room is around 65 decibels, a typical level of speech, the sound level in the adjacent room, the receiver room, will be approximately 20 decibels, barely audible. If sound levels are increased in the source room to 75 decibels, raised voice, sound levels within the adjacent room will also increase to around 30 decibels, audible. Sound insulation therefore describes the level of sound across a partition and not the level of sound within an adjacent room. If a new wall is to separate a bedroom or a room containing a WC from another room, it will need to have an improved sound insulation installed. There are two parameters used to describe the sound insulation of a partition. They are DW and RW. DW represents the sound insulation between rooms on site, and these figures describe the final site requirements and are specified by the clients and within building regulations. RW represents the lab-tested sound insulation of an element making up a partition wall or floor type. Flanking and other factors mean that lab-rated sound reduction levels will not be achieved on site. This means that conventionally there is a 5 to 10 decibel reduction between an RW lab tested figure and an on-site WD figure. This conversion can be relatively complex since it takes into consideration receiver room volume, receiver room reverberation times, and the area of the separating partition. This conversion should always be calculated. There are many different products and solutions on the market, and gaining advice from a manufacturer or building control body is recommended. Building a new wall to subdivide a room or create a new room can affect the means of escape from fire. If in doing so, a situation is created whereby the route for leaving an existing or new room is only possible through another room, then an egress escape window from the existing or new room, the inner room, will be needed, as well as possibly one or more smoke alarms. If the floor level of the inner room is greater than 4.5 metres above ground level, as with the top floor of a typical 3-storey house for example, the use of an egress window may not be safe, and therefore an alternative solution will need to be sought. This may well be one that does not create an inner room situation in the first place. Some walls around stairways, typically in houses 3 storeys or more in height, need to have fire resistance to ensure a fire in one of the rooms off of the stairway doesn't unduly affect the means of escape from other rooms in the house. In other houses, such as in 2-storey houses, the walls may not need to have any particular fire resistance, but would still afford some protection to the stairway by containing the fire and smoke for a period of time. The impact of the removal of an internal wall on fire safety should be carefully considered. In 2-storey houses, the removal of such a wall could normally be compensated by the provision of mains-powered interlinked smoke alarms and egress windows from the other rooms off the stair. However, in houses of 3 storeys and greater, this compensation may not be sufficient. The exact features needed will vary on a case-by-case basis. A new wall, including any door leading through it, which separates a room from the stairway, may need to have adequate fire resistance, typically in 3-storey houses, and in the case of a door, be self-closing. To find out more on fire safety, we recommend reading RIBA's fire safety information, which can be found on www.architecture.com/campaign/Grenfell-Tower. Work to provide a new internal wall generally requires approval under the Building Regulations 2000. In the case of conversion projects, adequate separation in terms of fire resistance and thermal insulation should be provided between the new habitable space and the remaining space. Any door provided in such a wall should have adequate fire resistance and be self-closing. Depending on the use of the new habitable room, the new separating wall may also need to provide sound insulation. In the following slides, we will cover the fundamental aspects of load-bearing and non-load-bearing walls. Internal walls can be constructed of different materials, such as a timber frame, metal frame, or masonry. When constructing a new internal wall, it should be supported by something strong enough underneath, whether the wall is load-bearing or not. Non-load-bearing is defined as follows. With timber or metal frame walls, it is normally acceptable to support them on the existing floor joists, not the floorboards, either by providing a double floor joist underneath if they run parallel, or across the existing joists if the floor joists run at 90 degrees to the wall. In both cases, there may be circumstances where additional support may be needed. Therefore, it is strongly advisable to ask a structural engineer or a surveyor to check the adequacy of the floor joists. With masonry walls, which are heavier, the floor joists may need to be larger, or, more likely, it may be necessary to provide a new beam. If the flooring is of a concrete construction, it will be difficult to ascertain the thickness and strength of the floor. Therefore, unless it is certain, the lightest possible construction is advisable. Load bearing. The support needed for a load-bearing wall is likely to be more extensive, depending on the load the new wall will be supporting. But for a new wall in an upper story of a typical house, providing support to the wall from the existing floor joists is unlikely to be adequate, as the self-weight of the wall plus the load it supports will probably be more than the joists are capable of supporting. This may mean introducing a new beam, which itself should be adequately supported. For a new wall at ground story of a typical house, the support needed will depend on the existing floor construction. If it is a timber floor, then similar considerations for a new wall in an upper story will be relevant. Alternatively, a new foundation can be provided beneath the floor, although the work in doing this may be difficult. A new foundation is also likely to be needed even if the floor is of concrete construction, unless the floor can be shown to be adequate enough to carry these new loads. A new wall built off a new ground-bearing foundation or slab should be provided with a damp-proof course, DPC, at least 150mm above ground level. If the wall is formed through an existing concrete floor, care should be taken to ensure continuity of the damp-proofing by linking the damp-proof course with any damp-proof membrane in the existing floor. This is a difficult procedure to accomplish without damaging the membrane or floor. If the new wall passes through an existing timber floor, the key thing to pay attention to is ensuring that any new timber that is in contact with or supported by the new wall is above the line of the damp-proof course. Also, if there is ventilation in the void under a suspended timber floor, then air bricks in the wall are likely to be needed to maintain airflow through the void. In this session, we'll be paying close attention to 4 different types of wall construction products. They are block work, dry lining, plasterboard, steel frame systems, SFS, and advanced walling systems. Firstly, we take a look at block work. Blocks are constructed using concrete or cement. They may include a hollow core to make them lighter and to improve their insulation properties. They have been in use since the 1930s, when they were commonly used for the inner leaf of cavity walls. At this point, they were made from an aggregate of stone and industrial waste, such as clinker or breeze, hence the term breeze block. They are now used for a wide variety of purposes, such as the construction of load-bearing walls, retaining walls, partitions, and foundations. A standard block is 440mm by 215mm, the equivalent of 3 bricks high and 2 long, the maximum size that one person can comfortably lift. They are available in a range of widths from 50mm to 300mm. The kind of block selected for a particular application will depend on its density, load-bearing characteristics, appearance, weight, and handling properties, or thermal characteristics such as U value or thermal mass. Looking at the table on the slide, you can see that blockwork is a solid, strong material with effective soundproofing properties, whilst also being fire resistant. However, blockwork can be expensive. Installation can be time-consuming, more trade workers will be required on site, and it produces considerable debris and waste. We now turn our attention to dry lining, or plasterboard as it's commonly referred. Dry lining is a system that can be used for cladding the internal faces of buildings, such as walls and ceilings. Plasterboard is attached to the internal faces, creating a smooth surface that finishes such as paint can be applied to directly. A wet plaster finish is not required. Dry lining requires less technical expertise than traditional plastering and requires little water, hence the term dry lining. Plasterboard is available in a wide range of lengths, widths and thicknesses. The larger the plasterboard, the fewer the joints, but the harder it is to handle and fit. Plasterboards have a core of plaster which provides good acoustic and fire insulation. Fibres can be added for extra strength and durability, and the plasterboards can be treated with wax to provide water resistance. Plasterboards can be fixed directly to the internal face of a wall or a ceiling, or can be fixed to a secondary frame of metal or timber and attached to the internal face. Plasterboard is praised for its economical credentials and improved thermal efficiency, but its downfalls lie in its complexity of installation and the fact that it can be easily damaged, particularly in busy construction sites. It is also important to note that dry lining does produce extensive waste. Now we take a look at steel frame systems. Steel frame systems, SFS for short, are modern structural systems which are designed for the easy, fast construction of modern frame buildings. They allow steel columns, steel beams, and other structural components to be assembled in a framing pattern, thus creating supports for floors, roofs, walls, and other internal parts like partitioning and cladding. SFS systems are providing an increasingly popular choice in modern buildings compared to other construction materials. However, installation requires more tradesmen on site, and there is complexity surrounding fire stopping. This should be closely considered. Finally, we explore how a modern approach to wall construction can help to overcome a multitude of issues within the built environment, allowing for more sustainable outcomes. Many of you won't be familiar with this wall system, but looking at the slide, you will notice that it's constructed of a concrete-based inner mixture, which is encapsulated by 2 fibre cement boards. It has inherent insulation, acoustic and fire ratings in the form of a lightweight, solid panel, which allows for the direct application of finishes, including tiles and paint. It is not affected or damaged by water or mould, and can be installed before the building is watertight, making it suitable for pre-build Cat A and Cat B installs. This factory-made system can offer an alternative to more commonly used wall construction materials, including blockwork, SFS, dry lining and plasterboard systems, risers and dry risers and smoke risers, smoke shaft, lift shafts, concrete core, and stairwells and bathroom pods. The following animation demonstrates the advanced walling system's off-site manufacturing process, which is a multi-step process. Raw materials are placed into batch hoppers. Materials are then weighed and put into a mixture according to specific properties. Water and additional materials are then dispensed into wall panel moulds. After a curing period of 5 to 10 hours, the advanced wall systems are packaged and prepared for site transportation. Much has been said about how the construction industry can play its part in the reduction of carbon emissions throughout every stage of the built process. A major way in which construction companies can look to mitigate their climate impact is to review the types of building materials they use and look for modern alternatives, which have a lesser impact on the environment, both when it comes to emissions and how they can reduce the amount of extraction inherent in building. Modern methods of construction, MMC, have many advantages, but their environmental impact may be the most important of all. Factory-controlled, off-site production leads to a huge reduction in waste, fewer emissions from the site vehicles, as well as a higher quality of product which will naturally last longer and not need replacing as quickly. We now explore the notion of fire safety. As we mentioned before, fire safety is one of the most important considerations for all projects and should be at the forefront of your mind when planning and building your development. Fire protection systems are a legal requirement, and meeting those responsibilities includes choosing the right materials for your building. This advanced wall system is A2 to S1 D0 rated. This is due to its structure, which is cementitious and inert. During installation, fire-rated adhesive must be used. Additionally, the walls are installed up to the structural soffit, reducing costly fire stopping. You may wonder how many hours of fire resistance this advanced wall system provides. The wall system comes in two thicknesses, 75mm, which provides over 2 hours of fire resistance, and 100mm, which provides over 4 hours of fire resistance. Overall, using this system allows you to build 6-metre firewalls without the need of additional support, which will achieve a fire rating of 4 hours or more. Before specifying any building material, it's crucial that you're aware of any health, safety and long-term maintenance issues that may be apparent. With this advanced wall system, the robust construction means that it's less susceptible to damage. And this includes damage through water or mould. This means that the wall system can be installed before the building is watertight, making it suitable for pre-build Cat A and Cat B installs. In the event of any boards getting damaged during construction, any impact damage can be filled. For more extensive damage, sections can be cut out and replaced rather than having to replace the boards entirely. If there are instances where the wall system is fitted in double, triple height spaces, Site Regulation 9.2 of the CDM Regulations 2015 regarding the principles of prevention from falls. Whilst there are clear advantages with advanced wall systems, it is important to note that most systems are, at present, non-load bearing. Therefore, they cannot support the floor roof loads above, and they're not part of the structural frame system. Please note, advanced walling systems are being developed further, and in time, fully tested load-bearing prototypes are expected in the market by 2022. We're now going to explore how advanced wall systems compare to two alternatives: plasterboard and AAC block. There is a lot to digest in this slide, so please take a moment to pause the video and take it all in. As you will be able to see, this advanced wall system outperforms current industry standard solutions across a range of key factors, including fire rating, acoustic rating, wastage, and more. Please note, this advanced wall system can be designed by the technical team to meet any U-value requirement. In the following slide, we list a series of considerations for you, the specifier, when it comes to the specification of building materials for internal and external walls. Firstly, we explore labour. Reducing the amount of tradespeople on site can make for a much more efficient process. Time and motion studies carried out on previous works show that by using an advanced walling system as a blockwork replacement or an alternative to a steel framing system, SFS, you can reduce labour hours needed for installation by more than 55%. Secondly, we have program time. Selecting systems that are easily installed and that contain pre-bonded joints can significantly reduce program time. Not to mention selecting a system that allows for a direct application of finishes. Cost is also a major consideration. It's important to specify a product that allows for speed of installation, application versatility and resistance of impact damage in order to drive down overall budgeting cost. Some wall constructions can fall victim to water damage, so you should select a solution that is not affected by water, mould or any other wet scenarios. Not only does this provide increased longevity, but it allows for installation at any stage of the project, even before building is watertight. Sustainability is also a key consideration. Modular, off-site manufactured products that can be recycled are the best way to ensure more sustainable outcomes. It is suggested that more and more specified building materials will be manufactured off-site as the UK works towards its net zero goals. And finally, we have efficiency. Reducing the amount of wall types on-site and the number of trades you need to fit into the overall construction programme is an effective way to ensure a more efficient approach. All of this can be achieved through the use of advanced walling systems. We're now going to take this moment to demonstrate how an advanced walling system can be used on-site to drive up efficiencies. In this first case study, the advanced walling system was supplied and installed into a number of areas, including an undercroft car park, a spa, a leisure facility and penthouse suites at a 369-unit residential development in Manchester. The developer, Property Alliance Group, has commended the advanced walling system for its programme-saving qualities, which led inevitably to cost savings. These benefits include early on-site commencement of the works, elimination of the risk of water damage to the partition wall due to its weatherproof nature, and the elimination of additional items such as pattressing, which are commonly encountered when installing a plasterboard system. Our second case study comes from a development in Manchester, where the advanced walling system was supplied and installed into the basement and ground floor of 2 plots of the Angel Meadows development, Manchester, with Westfields Construction. The site team noted that the advanced walling system met all the primary reasons for the selection of the system over blockwork and other partitioning systems. These benefits included wall stability and integrity, simplicity and speed of installation, significant programme savings and the ability to install in all weather conditions without the need for a watertight site. By now we hope you've come out of this with a fresh perspective on the notion of designing out waste within the built environment. We also hope you've developed the understanding of different wall systems, both new and traditional, and that this has helped you to consider alternative methods for future projects. And finally, we hope this has allowed you to think differently about the products and methods you specify to ensure a safer, more sustainable future for all UK construction projects. We have been Specwall. We really do hope you saw value from the content within this presentation. If you have any questions or queries, here are our contact details. We encourage you to get in touch with one of the technical team members should you require any further assistance. Once again, thank you for attending How Advanced Walling Systems Can Produce Sustainable Outcomes in a Built Environment. Delivered to you by Specwall.